Hello and welcome to another geometry read along. Today we are covering section 3.3, the Pythagorean Theorem and right triangles, possibly one of the most important, most broadly applicable in everyday scenarios topic there, right triangles. They are everywhere. Anytime you want to build something, right triangles are involved, such as this guy, right? We have a building here, has the dimensions as shown. If the rafters have a 2-foot overhang, that is to say the little parts that come support the roof, determine the length of a rafter and the number of squares of shingles required to roof the building. Note, a square of shingles covers 100 square feet. That's a big square of shingle. Okay, so we know the building is 48 feet long. They're saying the rafters go 2 feet over in either direction, so be sure to add that if you want to find the size of this triangle. But, okay, I know this length and this height. I could find the area of this triangle, but how do I find the area of the actual roof? That is what we are going to determine today with the Pythagorean Theorem, which relates the lengths of the legs and the hypotenuse of a right triangle, perhaps the most famous of all theorems in geometry. Okay? It is named for the Greek mathematician Pythagoras, circa 500 BC, who presented a proof of the relationship. However, there is no question that the results of the theorem were known and used for hundreds of years before his time in several different civilizations, including Egypt, Babylon, and ancient Chinese. He's just the first guy that wrote the proof for it, but others have very much demonstrated. And here it is in its shining glory, the Pythagorean Theorem. The sum of the squares of the lengths of the legs of a right triangle is equal to the square of the length of the hypotenuse. Okay? So we are squaring the legs, make sure it's a right triangle, and that will be equal to the square of the hypotenuse. Again, the hypotenuse always referring to that longest side across from the right angle. Or, algebraically, you could write it a squared plus b squared equals c squared. We can verify Theorem 3.8 using areas of triangles and squares as shown next. So here is one possible proof for the Pythagorean Theorem. There are many available, some of which show up in the exercises to this section. So we're going to show that the Pythagorean Theorem holds true for right triangle ABC in figure 23A. So that would be down here. How do we do that? Arrange 4 copies of triangle ABC to form a large square as shown in the figure. So we have literally traced over and duplicated and rotated so that each of the square angles of my triangle forms the square corner of a larger square. And of course we want to make sure that these two triangle legs are collinear and they line up perfectly. So now, because triangle ABC is a right angle at C, x plus y equals 90 degrees. You can see x and y right here and here, or there and there, right? The two angles, that's triangle sum. Because angle CBH is a straight angle, CBH down here, and x plus y equals 90, we can conclude that angle ABG, so they're talking about this angle inside here. ABG is a right angle. Using similar reasoning, we find angle BGE, AEG, and EAB are also right angles. So they're saying that all of these 4 corners of this shape inside here must be right angles. Thus, AEGB is a square. Now, we will compute A, the area of square CDFH. CDFH is the largest one on the outside. Okay. And B, the area of square AEGB. That's the smaller one inside there, that tilted one, together with the areas of the 4 triangles. So CDFH would be A plus B, so the total length of the side squared. And if you distribute that out, A squared plus 2AB plus B squared. Area of AEGB plus 4 times the area of a triangle ABC gives us C squared, C and C, plus 4 times 1/2 AB will give us C squared plus 2AB. The area of the larger square must be the same as the area of the smaller square plus the areas of the 4 right triangles. Therefore, A squared plus 2AB plus B squared equals C squared plus 2AB. Subtracting 2AB from both sides, we have A squared plus B squared equals C squared. QED. Many geometric figures, as well as real-life designs and constructions, include right angles, providing opportunities to apply the Pythagorean theorem all over the place. So let's try a couple examples ourselves. Find the missing side lengths in each triangle in figure 324. We've got one here, looks like the hypotenuse is missing. Here the leg is missing, and here we have, we don't actually know any leg or side exactly, but we know their relationships. So we'll see what we can do there. In the triangle in figure 24a, the length of the hypotenuse is unknown. However, by the Pythagorean theorem, we have 4 squared plus 5 squared equals x squared. So that would be 16 plus 25 is 41. So x is the square root of 41. That's our exact answer. 41 does not have a perfect square, so it's about 6.4 inches. And do note we're dealing with actual lengths here. Length of a side can never be negative, so we'll always use the positive square root. Now, in triangle 24b, the length of one of the legs was unknown, so we can set that up as x squared plus 8 squared equals 12 squared. Okay, square those numbers, so x squared plus 64 equals 144. Subtract, x squared equals 80, and now x is the square root of 80. I don't know why they dropped the 0 there. Okay, which can be simplified to 4 times the square root of 5, or about 8.9 centimeters. Square root of 80. And in triangle 24C, none of the lengths of the sides is known, but a relationship between them is given. To find the lengths of all 3 sides, we will use the Pythagorean theorem. X squared plus the x plus 1 squared equals the x plus 2 all squared. So go ahead and distribute out those binomials. We'll have x squared plus 2x plus 1 equals x squared plus 4x plus 4. Combine like terms and move everything to one side to get a single quadratic equation, x squared minus 2x minus 3, which can be factored into x minus 3 times x plus 1. Using the zero product property means x must be either positive 3 or negative 1. And again, because the length of a side cannot be negative, x must be the 3 centimeters. Thus, x plus 1 is 4 centimeters, and x plus 2, of course, is 5 centimeters. Now, we can use that Pythagorean theorem to calculate areas of geometric figures as illustrated in the next example. Let's see how that works. Find the area of a square that has a diagonal 10 inches long. So here a square is given. If we had the side length, we would just square that number and be done, but here we're only given the diagonal. What do? Well, the diagonal and the sides of the square form 2 right triangles, as you can see in the diagram there. To find the length of a side of the square, we will use the Pythagorean theorem. In this case, s squared plus s squared, those are our a and b, equals 10 squared, or 2s squared equals 100. Divide both sides by 2, s squared is 50, which we can stop right there. You might think, oh wait, square root, find the length of just s. We don't need just s. we're after s squared in the end, right? Isn't that the area? The area of the square is s squared. It's 50 inches squared. Done. Oh, that's actually much easier. We don't have to introduce the radical. Now, the other useful thing with Pythagorean theorem is to work backwards as a test for right triangles. Okay? The Pythagorean theorem states that in a right triangle with legs of length a and b and hypotenuse length c, we have a squared plus b squared equals c squared. On the other hand, sometimes we need to determine whether a triangle is in fact a right triangle. There is a test based on the Pythagorean theorem that indicates whether or not a triangle contains a right angle. This test depends on the relationship among the three sides of a triangle. If triangle ABC has sides length A, B, and C, as in figure 326, so if we take a triangle, label it as such, and if a squared plus b squared equals c squared, then triangle ABC has a right angle at vertex C. If a squared plus b squared does not equal c squared, then triangle ABC is not a right triangle. We can verify this test in chapter 4. In fact, this is of such historic significance, the ancient Egyptians used this to square their buildings. They would take a rope and tie knots into it and hold it to form a right triangle, and they would adjust it so that the lengths were perfectly of 3, 4, and 5 units, knowing that that created a perfect right triangle. They knew that this corner was square, and thus they could use it much like a carpenter's square is used today. So let's try this test. Lengths of sides of two triangles are given. Determine if either triangle is a right triangle. We've got 11, 15, and 19. Okay, let's test. So we'll set A to be 11, B to be 15, and C to be 19. How do we know C gets to be 19? C is always the biggest one. Then A squared plus B squared equals 11 squared plus 15 squared, or 346. And C squared would be 19 squared equals 361. Ooh, not the same. A squared plus B squared does not equal C squared. The triangle is not a right triangle. So sad. All right, how about B? We've got 7, 16.8, and 18.2. So plug those numbers in for A, B, and C. We will get 7 squared plus 16.8 squared, which will be 331.24. And C squared, 18.2 squared, is 331.24. Hey! Those are the same, so because A squared plus B squared equals C squared, a triangle with side lengths 7, 16.8, and 18.2 is a right triangle. Way to go. If you want a shortcut list, this one I've referenced already here. These are called Pythagorean triples. We have the 3, 4, 5 triangle, far and away the most common Pythagorean triple. And the next 4 most common that are worth recognizing and knowing are the 7, 24, 25, and we've got the 5, 12, 13, and let's go one more. The 8, 15, 17. These are all worth knowing, worth adding to your notes, recognizing those Pythagorean triples. They are the most commonly used, especially on standardized tests and such. All right, now, in addition to those Pythagorean triples, the ones where they just have integers, values that work for the Pythagorean theorem, we also have a couple other special right triangles. Okay? 2 special right triangles that appear frequently in geometric applications, again, actual building and construction. First, consider an equilateral triangle. Recall that an equilateral triangle is also equiangular. So we have side lengths of S, S, and S, and all three angles are 1/3 of the triangle sum 180, aka 60 degrees for all three. Now, also, in Chapter 2, we saw that an equilateral triangle has 3 lines of symmetry. If we fold the triangle on a line of symmetry, as shown in Figure B, we form 2 identical triangles. Okay, just cut this guy in half, you get 2 triangles there. Because the angles on either side of the line of symmetry must be congruent, the angles in each triangle measure 30, 60, and 90. Right? This perfect line of symmetry will be perpendicular to that base. It will bisect this angle evenly, so we'll get 30, half of 60, the remaining 60, and a new introduced angle of 90 degrees right there. Thus, each triangle that is formed is called a 30, 60, 90 right triangle, or a 30, 60, 90 triangle. Right? Because the base of the equilateral triangle is bisected, that is, cut in half by the fold line as shown in Figure C, each 30, 60 right triangle has a base of S over 2, right? So this was side length S. We cut it in half here, so this is S, and this is half of S. Now, using the Pythagorean Theorem, we can determine the height h of any 30, 60 right triangle in terms of S as follows. We'll write Pythagorean Theorem. Keep in mind h squared is one leg, half S squared is the other leg, and the hypotenuse now is S squared. So h squared plus S squared over 4 equals S squared, or h squared equals 3S squared over 4. So taking the square root, h is the square root of 3S squared over 4, or we can simplify that one step further. H equals S times the square root 3 over 2. The next theorem summarizes this discussion. So let's put it all together. Right? Add this guy to your notes. The shortcuts for a 30, 60, 90 triangle, or 30, 60 right triangle. In a 30, 60 right triangle, the length of the leg opposite the 30-degree angle is half the length of the hypotenuse. Okay? Length of the leg opposite the 30 is half. The length of the leg opposite the 60-degree angle is root 3 over 2 times the length of the hypotenuse. Right? So notice there, the 30, the smaller angle is across from the smaller side. We already knew that from our triangle inequalities. So the 30 is half whatever the hypotenuse was. And across from the 60 is the root 3 over 2. The fact that the relationships stated in Theorem 3.9 are true for any 30, 60 right triangle means that if we know the length of any one side of such a triangle, we can find the lengths of the other two. Okay? If we know it's a 30, 60, 90 triangle, and we know one measurement, we can find instantly the other two. We don't have to go through Pythagorean Theorem all over again. Now, one thing I will also point out is remember how we got this triangle. It's half of the equilateral triangle. So you could also use this to recall that the height of an equilateral triangle will be square root 3 over 2 times the side length equilateral triangle. That can save you some time in finding its area. So let's practice that. Find the missing side lengths for each 30, 60 right triangle in Figure 28. Okay? Here we're given the hypotenuse of 4, and this one we have the longer leg, 5 centimeters. So using the notation in Theorem 3.9, we find that S is 4 inches, so S over 2 would be 2 inches, and square root 3 over 2 times S is root 3 over 2 times 4. The 2 and 4 will become 2 times square root 3 inches. Therefore, the leg opposite the 30-degree angle is 2 inches, and the leg opposite the 60-degree angle is 2 times square root 3 inches, or you could say that's 2 root 3 inches. Now in B, remember we're given the leg. Which leg is it? This one is across from the 60-degree angle. So we know that root 3 over 2s equals 5 centimeters. So s is 5 times that reciprocal fraction, 2 over root 3, or 10 over root 3, which will rationalize the denominator, multiply both by root 3 over root 3 here to get 10 root 3 over 3. And then s over 2 will be half of that, which is easy enough. Just take half of the 10, 5 root 3 over 3 centimeters. Thus, the leg opposite the 30-degree angle has a length 5 root 3 over 3 centimeters, and the hypotenuse has a length 10 root 3 over 3 centimeters. Now, for the other special right triangle. A similar relationship exists between the lengths of the sides of the right triangle formed by folding a square along a line of symmetry containing one of its diagonals. Okay? So if we take a square and fold it in half diagonally, we get this lovely symmetric triangle here. Because the angles formed on either side of the fold line must be congruent, and because they also are complementary, we know that each of these acute angles must measure 45 degrees. Thus, each of the triangles formed is called a 45-45 right triangle or a 45-45-90 triangle. Notice that each triangle formed is also a right isosceles. That's good to remember. This is the one and only right isosceles triangle. It is the special 45-45-90. We can once again apply the Pythagorean theorem to determine the length of the hypotenuse C in a 45-45 right triangle in terms of the length of one of its sides, S, as follows. So since s squared plus s squared will equal c squared is 2s squared, or c would be s times the square root of 2. Summarize all right here. Make sure you add this theorem to your notes with all of the juicy details on our second special triangle. In a 45-45 right triangle, the length of the hypotenuse is square root 2 times the length of a leg. Okay? Hypotenuse is root 2 times a leg. And as was true for the 30-60 right triangle, this theorem allows us to find the missing lengths of two sides of a 45-45 right triangle if we know the length of any one side. This is more powerful. Okay? For any right triangle, we can use Pythagorean theorem if we're given two sides to find the third. If it's a special right triangle, a 30-60-90 or a 45-45-90, we can find two sides if we're only given one. Okay? That's the difference. All right, let's practice with the 45 guy here. And we're going to use it to find the area to the nearest square inch of parallelogram ABCD. In this parallelogram, notice we are given the length of one base, but we don't know the height of the parallelogram. We have its other side length and the angle here. So, what do? Take a look at figure B there. We convert the dimensions to inches. That we're not dealing with feet and parts of feet, okay? All inches. And draw in the height to the longer side, right there. Now triangle ABE, this one here, is a 45 right angle. The other one has to be 45, so it's a 45-45 right triangle. So we have h root 2 equals 42, right? The side length times square root of 2 will give us the hypotenuse. Or solving for h will be 42 divided by square root of 2. And therefore the area of ABCD is base times height. So we'll take that base, 86 inches, times height, which is 42 over root 2. Again, does this number have to make sense yet? No, I wasn't asked to find the height. Just use it as is, simplify only at the very end, and round only at the very end to get a total area of approximately 2,554 inches square. Now, we have shown that if a triangle is a 30-60 right triangle or a 45-45 right triangle, and if we know the length of one side of the triangle, then we can determine the lengths of the other two sides. We will generalize this technique in Chapter 6 so that given the measure of one angle of any size and the length of one side of a right triangle, we can find the lengths of the other two sides. Hint, hint, this is called right triangle trigonometry. So if you've ever heard sine, cosine, and tangent, that's where they come in. They generalize beyond just the special right triangles. Okay? But we don't need to concern ourselves with that for this moment. Let's take a look back at that roofing problem. Following figure is an end view of the roof portion of the house. Remember, the rest of the house sits underneath here. Because a rafter forms a right triangle with the end of the house, we can apply the Pythagorean Theorem to find the length of a rafter, x plus 2, this guy here. We have 24 squared plus 10 squared equals x, so we're going to use the half the width of the house, okay, as our base, one side of our triangle. We know the height is 10, so we plug those two values in, solve for x, which is the hypotenuse of our triangle, but remember they said the rafters go 2 feet further down. So we'll have to solve for x first. Okay? That'll be 676 is x squared, or square root that, 26 feet. Therefore, the length of the rafters is x plus 2, or 28 feet. Each half of the roof is a rectangle measuring 60 feet, that was the length of the house from the original diagram, by 28 feet. So hence the total area of the roof is given by twice, both sides, of 28 times 60, or 3,360 feet square. The number of 100 square foot roof tiles that we will need is that divided by 100, or 33.6. Thus, the roof requires 33.6 squares of shingles, which means you will need to buy, of course, at least 37 of them. And then one more glimpse into the geometry all around us. Carpenters, bricklayers, and other builders frequently make use of the test for right triangles to lay out a square corner. They may mark off a distance of 3 feet on one wall and a distance of 4 feet on the adjacent wall as shown. So you'll just measure out 3 feet from the corner there, make a tick, 4 feet, make a tick, and now measure between those 2 points. If the corner at point A is to be a right angle, then the distance from B to C must be exactly 5 feet, since 3 squared plus 4 squared equals 5 squared. This 3, 4, 5 triangle is probably the most commonly used right triangle, but any multiples such as 6, 8, 10 could be used. Hey, that's what I said. Other common right triangle ratios such as 5, 12, 13, or 8, 15, 17 can also be used to square a corner. There they have it. Good job, textbook. I didn't even need to bring it up myself, but there you have it. Once again, how common these 3 Pythagorean triples are, because they're so easy to calculate. All right, and that's going to do it for this section. Thank you for reading along with me. So long, farewell, enjoy the rest of your day.